Thank you all for coming to the afternoon colloque. It is my pleasure to introduce today's speaker, Peter Pivovarov from University of Missouri, Columbia. Peter has received his PhD in 2010 from University of Alberta at Edmonton with Nicole Tomczak Jagerman. And since then, he had an answered postdoctoral fellowship at Texas A&M and spent the semester at the thematic program in geometric analysis, asymptotic geometric analysis at the Fields Institute, after which he joined the faculty of mathematics at the University of Missouri. Since 2012, he is a professor there. And he is specializing in the area of asymptotic geometric analysis, and the one important feature that will be represented as well in today's talk is he combines techniques from probability, function analysis, and convex geometry toward obtaining interesting geometric inequalities. So, Peter, please.
Oh, thank you very much for this kind introduction and invitation. It's an absolute pleasure to be here in Montreal. It's been some years since I've been here, so it's great to be back. Part of the subject I'm going to talk about today is very old and classical, as old as geometric probability itself, and some of it is more recent. And so when I started thinking about where to start this talk, I thought I'll structure it in sections and maybe start with some gems from the history of geometric probability. I decided I should start really with one of the earliest problems is motivation, right? It's Friday, it's 3:30. Naturally, you should hear the history of this subject from 1864. Okay, so in 1864, Sylvester posed this problem called his 4-point problem. It was posed in the Educational Times in London. Maybe we have to read it and parse it a little bit. Older English. So show that the chance of 4 points forming the apices of a re-entrant quadrilateral is 1/4 if they be taken at random in an indefinite plane. Okay, so maybe we'll read it again. Maybe apices, apex, let's trade that for vertex. Re-entrant quadrilateral, re-entrant quadrilateral. Okay, quadrilateral, we can agree. Re-entrant, why don't we say non-convex? Okay, so take 4 coins out of your pocket, throw them in the air, and look how they land. Do you get a genuine quadrilateral or a non-convex quadrilateral? Okay, so the claim is the probability that you get a re-entrant one, a non-convex one, happens 1/4 of the time. Okay, so this was posed in the Educational Times. Readers submitted answers, and no consensus about the number 1/4. Ingleby said, well, it's less than a half, upper bound. Okay. Another submitted answer, no, not 1/4, but 1/3. Cayley, helping Sylvester, says, in fact, it's 1/4. De Morgan, so not that De Morgan, but yes, that Cayley. De Morgan says, no, it's 1/2. Someone else is pretty sure it's 3/8. Not quite so sure that they want to attach their name, but definitely not 1/4. And 35 over 12 pi squared by Wilhouse. Okay, so you can start to think about maybe, are they wrong answers? Or maybe if you parse the question again, maybe it's the wrong question, right? What's the word chance mean, right? If I take 4 coins out of my pocket and throw them in the air and they drop, it shouldn't affect the probability if I do this on the other side of the room. I should have some translation invariance, right? But it should probably also be some kind of uniform density. Am I doing this on the plane? What's the underlying probability measure, right? So well before sort of more rigorous meaning of what's the probability measure or space you're going to be using for this problem. So it's natural to think you would use something uniform, but if I'm working with a convex operation, I want to know when, these land in sort of convex position or not. I might want a sort of ambient convex shape to work in. And I might want to bound it so that I can put a genuine probability density on the set. But then the shape I use is going to, of course, affect the probability if I use a square, a circle, or a triangle, etc. So if you look at these and analyze these questions, or this question with this perspective, then you're led naturally to restrict, for example, to compact sets, retain the translation invariant, and they also impose a convexity condition. And if you think a little bit more, the 4-point problem is actually a 3-point problem. Okay, because once I've selected 3 points, I want to know if the 4th one is a 4th vertex or it lands in the triangle generated by the first 3. But if I condition, and I'm using just a uniform density on a convex set, that's proportional to the probability it lands in the triangle, right? And that is just a multiple of that area, right? So the 4-point problem is a 3-point problem, and with all those considerations, Blaschke took all these into account and resolved this problem in the plane, and it was led to the following quantity. Okay, so I look at the average. I call M for mean. It's the expected mean value of an area of a random triangle. I use con for convex hull. I have 3 points. I toss the first 3, right? That's the average area of the first 3. And then I'm asking, what's the probability that the 4th one lands inside there? Well, that's just the expected area here. So I divide by a volume or an area of K to the 3 for the probability space. And I'm going to make this ratio in between 0 and 1. So you throw an extra power of the area of K in the denominator. Okay, so this is just some iterated integral. It's in the plane. You're in R6, 3 copies of that. It's on a product space, perfect function. And here's some examples. I toss 3 points in the disk, in the square, in the triangle. And you can check that this quantity is actually invariant under invertible affine transformations, certainly allowed to shift. If I did a variable change with some linear map, I would just pay a price of a determinant. It would come out in the wash 3 times in the denominator, and once from the convex hull. So that's the 4th power. And it's also continuous. There's a compactness argument. It says it has maximizers and minimizers. What are they? Circles minimize this quantity. Triangles maximize this quantity. Okay, so this, I think, is a very elegant way to address this question, address all the sort of deficiencies in the question. And now it's not one probability, but it depends on the shape of your probability space, and the range of numbers are between these 2 values. What you would get if you were sampling the points in a triangle, or what you would get if you were sampling the points in a circle. Or, I don't have to specify the size of these because I have normalized, and I don't have to specify what position or image of these because there's some affine invariance. Okay, so circles are minimizers, triangles are maximizers. Okay, so how to prove such a thing?
Do we know the values for the circle and triangle?
You can compute them. I don't have them in front of me.
But do they correspond to the one that were published in the newspaper by...
I have to do the computation to tell you an updated answer.
Thank you.
I have abandoned the exact values. Okay. For me, I'm thinking of the function as a function of shape. So, maybe some are right if they use one of these models, but I don't know the exact values corresponding to the shapes, but okay. Okay, so how did Blaschke prove this? Symmetrization processes. So Steiner symmetrization is something classical used, in 1830s by Steiner to prove the isoperimetric theorem, right? This is a volume or area preserving transformation. I think about fixing a direction. That's the vertical direction here. I think about a line perpendicular to that. For any line parallel to this direction that meets my body, I find the midpoint. I slide them down. So the midpoints all lie in a line. In this way, I introduce a reflectional symmetry, preserve area. Originally used to show this decreases perimeter and fixes area to solve the isoperimetric problem. The isoperimetric problem will show up again in this talk in a few places. But for this problem, it decreases this mean value. Okay, and more rigorous compactness arguments about iterated symmetrizations converging to a disk or a ball of the same area or volume in higher dimensions came later. But if you've ever made a snowball, you can agree that if you do this in the right directions, you'll get at sort of a round extremizer. In this talk, I'm going to call K star a ball. It's going to be a ball of the same area or volume, depending on the dimension, as the set that I started with. Okay, so I'll move from circle to K star. That will now be a ball. That's the lower bound. And the upper bound is a related process called shaking. And what you do is same process with the lines meeting the body, except you don't center them on this hyperplane. You just drop them so that one endpoint is on a line. So maybe more surprising is that if you take your ball of snow and drop it in the right orientation several times, you'll get yourself a pyramid. Okay, so this works in the plane. The process also will take you to simplices in higher dimensions. But one of these methods has much greater reach than the other in that Steiner symmetrization and problems with lots of rotational symmetries, right? This is a much more applicable method, right? The the Steiner process than the shaking process. Okay, so you can ask, this is in the plane. Is it really particular to the planar case? So what about higher dimensions? So it turns out half of this goes very well, and the other half, it's still kind of a mystery. So I'm going to call m the same mean value. I'm going to modify it a little bit because it's more impactful for what's coming later. I'm going to take a simplex now, convex hull of n plus 1 points in Rn, and I'm going to insist one of the vertices is the origin, and then the other n are random. Okay, I normalize in a completely analogous way. I use the same notation just to not have extra symbols. And now this quantity is similarly affine invariant, has maximizers. You can look at what happens with the lower bound. You should get a ball. This is a theorem of Busemann from the 50s. It's called his random simplex inequality, and it says the expected volume of a random simplex generated by the origin and n independent random points drawn from a convex body is minimized for a round ball. Okay. The upper bound is still at the stage of a conjecture. Okay, so mathematicians of the day are certainly forgiven for not solving the higher dimensional case because it's still unsolved. Okay, and why is it still unsolved? Even a 1-point problem for the upper bound is a hard problem. So what do I mean by that? Imagine I want to estimate the area of this random simplex. The angles aren't going to be so crucial, but what comes into the game for the volume computation is the length of these vectors. Now, there are many problems in which this is a main obstacle, knowing the expected Euclidean norm of a point in a convex body. Okay, so this has come up in a bunch of volumetric problems about convex bodies. The most famous is probably a formulation of what's known as Bourgain's slicing problem about finding lower bounds for areas of slices of convex sets. This is naturally related to norms of points. Okay, so that problem shows up in many problems about convex bodies. This was worked on by Bourgain and many others. It shows up in questions in theoretical computer science. When you want to sample from a high-dimensional convex body, naturally you need control of parameters associated with those bodies and things like norms of points. Okay, so the answer is still very far from identifying a sharp extremizer that a simplex in n dimensions, right, is going to be the extreme body, because it's hard to even estimate the dependence on dimension of these quantities. Okay, so a lot of progress went into this problem and related problems about estimating, for example, if I normalize the right way, the nth root of this quantity of this mk. And there are actually quite serious breakthroughs. I think you had a series of lectures or a lecture by Yansui Chen, who made progress on one of these problems coming from high-dimensional statistics or different field. And very recently, Clartog and Lahek made progress on this constants in Bourgain slicing problem. So this is actually something very recent that I mention here simply because I find it quite remarkable that this problem is, you know, still out there from okay, Blaschke's resolution, essentially, you know, maybe not formulated exactly like that, but in various guises. What I do want to talk about, though, is sort of the reach of the lower bound. So the lower bound is something, okay, proved in the 50s. It goes along the same lines. You still use this, prove this inequality using Steiner symmetrization. So there's a resemblance in terms of the method with the standard isoperimetric theorem, volume preserving transformation, Steiner symmetrization that decrease quantities. But the result itself is actually very important in other inequalities that themselves have implications for the isoperimetric inequality. Okay, so I have successfully completed part 1. Let me ask you if you have any questions. I want now to move from a question about, you know, random triangles to sort of downstream impacts, the reach of these inequalities. So it's a good time for me to pause if you have any questions about the notation, anything. I don't see, so I will continue. 2 is about determinants. So the idea here is you can sort of recast this problem of sort of cute solution to a problem about random triangles as a statement about determinants. But naturally, if it's about determinants, right, that's going to show up as a Jacobian in all sorts of places. Okay, so there are downstream impacts of these inequalities, and I think one of the most famous is the Petty projection inequality. Okay, so this is something that Petty proved in the 70s, One essential ingredient was this Busemann random simplex inequality, that the expected volume of a random simplex is minimized on balls. And what did he prove? Okay, so it involves orthogonal projections. I write P U perp for the orthogonal projection on U perp. I write bars for volume, now in an n-1 dimensional subspace. And what it says is if you take a convex body, you project on a one codimensional subspace, raise this to the power -n, average with respect to the usual invariant measure on the sphere, then this quantity is always maximized on balls of the same volume as the body you started with. Okay, so if you want to maximize this projection average, you can't do any better than balls, and even better, this has some extra invariance. Okay, it's the equality is achieved for ellipsoids. Okay, so I'm not sure how widely known this is. I know two of you know this because it's fundamental. I've heard about this since graduate school. I'm not sure how widely known this is as an inequality. If I say Petty projection inequality, does this jump out to you? Okay, so why is this fundamental inequality in convexity? So why don't we look at comparable averages without these funny -n powers? Okay, so I claim that the inequality I wrote just below is an equivalent way to state the isoperimetric inequality. If I take a convex body and I project on codimension 1 subspace as an average, then this gets minimized on balls of the same volume. Okay, so the easiest way to understand that is maybe just to think of the plane. So you take a planar convex set, project on a line, measure the length, and average over all directions. So I've drawn a convex set, I project it on a line, and now the red line, any line perpendicular to in the plane U perp here, is going to cut the convex set into two pieces, and the perimeter, it cuts the perimeter into two pieces, right? When I cut it, no matter where I cut it, the sum is always the perimeter. So if I integrate over that length, I'm just integrating the perimeter. Of course, that depends on the direction. If I did this horizontally, I would integrate over a smaller width. But nevertheless, it's still just the perimeter I would integrate. But if I average over all directions, it's not going to depend on the direction. It will be a multiple of the perimeter. So this is a classic geometric probability argument that you turn into a rigorous proof of this. And so the inequality above with power -n, with the K star symbol, that's a ball. These averages don't see anything, right? It's just a constant. But with the -n, just a simple application of your, Holder's inequality or Jensen's inequality says the power -n, this is a stronger statement than the one below. So you directly get the isoperimetric theorem, certainly in the plane. And the Cauchy perimeter formula is actually a Cauchy surface area formula. The right generalization is projecting on codimension 1 subspaces and averaging. So it is a legitimate strengthening of the standard isoperimetric theorem. I've stated this by saying the perimeter gets minimized on sets of the same area, but of course you might think about it as fixing the perimeter. I give you a piece of string. How do you enclose the biggest area? Of course, you use a circle. Those are companion statements, of course. So the added feature of this inequality is that you don't just have the disk as the equality case. You pick up ellipsoids. So it's an affine strengthening of the isoperimetric inequality. Okay, and among other things, Petty used the Busemann random simplex inequality to prove this. Okay, so also quite interesting, who was Petty? So the inequality is the same, that's the same one. Absolutely remarkable life. Was born in 1923, served in the Second World War, fought in the Battle of the Bulge, was wounded, returned in time for the drive across Germany, completed his PhD with Busemann in the 50s, worked at Lockheed for the satellite program, was a professor at the University of Missouri for almost 30 years, retired in the 90s. About a year ago, I saw in the Columbia Missourian an obituary for Clinton Petty, and I was absolutely shocked that this happened, 2 years ago now, okay, 2020. He died in 2021, and I saw the obituary online like a year and a half after he died. But I was shocked that, this is an obituary I'm reading essentially. I'm working on inequalities directly related to what he's doing. So, the obituary mentioned all these things. It did not mention that he proved a considerably stronger form of the isoperimetric theorem. If I knew this in time, I would have written these people and told them, but okay, I forgive them for it. Okay, so this I think is a very cool story. Let me say maybe a little bit about what precedes this inequality. And I mentioned he did his PhD with Herbert Busemann. Petty projection inequality looks a lot like another inequality, not about projections, but about intersections, proved about 20 years before by his advisor. And what does it say for, okay, star body, I just mean the smaller positive homotets of my body are still inside. Even this can be relaxed a bit, but for example, I don't need convex sets. And what it says now is if I take this set K and I take not projections on one codimensional subspaces, but sections, I raise this now to take the n-1 volume raised to the power n. Then if I want to maximize this quantity, I can't do any better than balls. Okay, a ball of the same volume. Okay, so it looks formally very similar to the Petty projection inequality, but there's a different operation, a different class of sets. I trade projections for sections and the powers are different. Okay, so this one has actually a more direct link with the Busemann random simplex inequality. So I've written a nice formula here, one consequence of a Blaschke-Petkashian formula from integral geometry. If you like reading formulas, read the formula. If you don't want to read the formula, you can just think about polar coordinates. If you want to integrate a function on Rn in polar coordinates, you do it radially, fix a direction, which you associate with a ray or a line, right? And then the radial part. And imagine you had a function you wanted to integrate, and I don't want to integrate on lines, which are one-dimensional subspaces, but on one codimensional subspaces, on planes. Then I can do that at the cost of some Jacobian. And the Jacobian is the exact expression you see in the Busemann random simplex inequality. So here's a formula from integral geometry, which now lets me pass from sort of global information about my function to something about subspaces.
Star body, do you allow spikes? Do you allow
You allow spikes, maybe you want a continuous radial function, and this can also be relaxed, but for now. I'm assuming the origin's an interior point, for example, and my radius function is continuous, but I can have spikes like.
rays sticking out that have positive volume?
Yeah. Okay, so this lets me pass from sort of information globally about my function on the whole space to its substructures, right? Integration on subspaces. Okay, so the analysts in the room might sort of think about the Radon transform. You know, if you have a function like the indicator function of a star body and you integrate it on a subspace, right? This is exactly the operation in the Radon transform. Or if I want to do the K-plane transform, I will think of translates of that. Kindred inequalities were proved by Oberlin-Stein and Christ. Erwin Lutwak in a survey paper in the Handbook of Convex Geometry pointed out how you can prove the theorem of Oberlin-Stein using this result of Busemann. Christ had a very similar proof. I kind of consider the ingredients there, you know, in an analytic context, but it's very much mirrors the ideas in Busemann's proof. Okay, and you might also think how this is related elsewhere, right? Naturally, if I'm treating problems about restricting a function on subspaces and integrating, right? You could think about what's the best? Is this visible for everyone? I'll use this because I want to reserve that one. Think about drawing a random point from a rectangle, for example, and then projecting it on a line, right? If I want a random point and I project it on a line, right, I can choose from this range for my x coordinate, from this range for my y coordinate. When I project it, if I want to know the density of that sum, well, that's an integration problem, right? Because it's all those ones that come from this line, or if I'm in n dimensions and I project on a line, I'm intersecting with a plane. But I get the density of the projection of this random vector by integrating. So naturally, if I want to know, you know, how well controlled the sums of random variables are, right? If I had a point x1, x2 with two components and I just projected onto something like a1, x1 plus a2, x2, it's really an integration problem for the marginal density. And these quantities, what they say is you cannot really make them degenerate. They have some invariance, and they are always at most what you get for the ball. So if I projected all my mass on this line and I look at the density, that's a big value. But if I project on the vertical line, I'll have a small value. And if I average right? I won't pay the biggest price, right? On average, these are well controllable. And what's interesting here is I don't need a product. K is any set here, right? A star-shaped set is not a product, okay? So I'm getting away from independence. Okay, so that's the spirit of where you might use a result like this, okay? It's very similar to the sort of analytic context, but the probabilistic one will come up later, okay? So I'll make it here. Okay, so very good. We had an inequality about projections, an inequality about sections. There are natural dualities between these. The sort of standard dual operation in convexity is to define the polar of a convex body. Maybe I'll assume the origin is an interior point. Associated with that, I can form the set, right? The polar, I denote with a circle here. All the vectors y in Rn, for which the sup of the inner product with y and x is less than 1. If you prefer norm space language and you assume this K is already the unit ball in a norm space, the K polar is just the unit ball in the dual space. Now, in norm space language, you know, if you take a quotient, dual of a quotient, right? It's a subspace of the dual, right? In geometric language, the polar of a projection is a section of the polar. Okay, but this is a duality that's heavily based on convexity. Convexity is built into those definitions. So there are many problems in which a kind of duality exists for convex sets, for sets beyond convex sets where you really don't have convexity. And nevertheless, you see a kind of mirroring phenomena for projections, maybe for convex sets, and for sections for star-shaped sets. There's a long list of such problems. Sometimes these sort of fit under the umbrella of Brunn-Minkowski theory versus what's called dual Brunn-Minkowski theory about sections of star-shaped sets. I wrote just some examples here. Volume comparison problems, comparing volumes of bodies given lower dimensional information about sections or projections. So Fourier analytic approach by Koldovsky that unifies these problems, extremal inequalities like the inequalities of Busemann and Petty that I mentioned, the notion of mixed volumes or dual mixed volumes put forth by Lutwak. More recent activity around Minkowski problems. You don't need to know any of this backstory to understand this talk, but it's good to have one example in mind. And the two inequalities I just mentioned about projections and sections exactly illustrates this. Okay, there's sections, there's projections. They formally resemble one another. One is for convex sets, one is for star-shaped sets. Okay, and so let me pause and ask if there's any questions about implications of what I turn from triangles to determinants and transform those into statements about controlling projections and sections. Any questions? Okay, so as part of this research, there is an important family of bodies that in a sense captures information about both projections and sections. And the way to encompass both of these in sort of one notion is through the notion of what are called LP centroid bodies. Okay, so this is a notion introduced by Lutwak and Zhang in the 90s. And I'll first give you the definition of a dual of an LP centroid body. And the dual, I mean the polar, just the usual duality. These will be convex sets in Rn that are origin symmetric. They come with norms. They have dual norms. Okay, I'm in the convex world for now. And they're defined given a parameter p, and I'll write Zp for the centroid body and the polar symbol for its dual. And what I'll tell you is just the dual norm. And what it is just the LP norm. P is bigger than 1 here. It's a genuine norm of a linear function along the body. Okay, I look at all the y's for which this LP norm is less than 1. Okay, so quick picture, right? When P is infinity, the LP norm goes to the infinity norm. That's the max. That's exactly the polar that you saw before. It's just K polar. And if I do a quick sanity check where K is this red square, it's L infinity, the dual is exactly L1. I did this with P being 100, but on a computer 100 is just as good as infinity. So you really see the dual. Okay, when P is 2, it's an ellipsoid. When P is 1, it's just the dual L1 centroid body. Okay, so that's just playing with P norms. The notion is dual to the notion of centroid bodies. That's a much older notion, going back to Dupin and Blaschke, Busemann, Petty. I've drawn a picture of the L1 centroid body now without the polar. And what is it? It's a bunch of centroids. Centroids of what? If K is the square, I fix a direction, y. I cut my body in two pieces through the origin, perpendicular to this y. And I look at the centroid of that region. I change the y. Every time I cut, I get it in two equal pieces, plot the centroids. So the locus of all points obtained as centroids of the halves of k cut by hyperplanes through the origin is the centroid body. Okay, so you can think about plotting the coordinates of the centroid body, and what this ends up being is a sort of distance to a supporting hyperplane to my body. Okay, so the LP centroid bodies change this construction with a p parameter, and the dual ones are just the polars of these. Okay, so I've shown you the picture, right? The centroid body is a collection of centroids of halves of a body cut. It's inside the body, but the polarity relation reverses inclusions. So the ones that were outside, right, in the previous picture, right, the K is the starting body, and the blue ones they contain the original body. And this is just a feature of the duality. Okay, so that's a family of sets. You start with the polar body. You have this parameter P you can play with. And now, very curious fact, if you haven't seen it before, take the limit as P goes to -1 and scale by P plus 1 over 2. What do you get? I wrote it here. You get the slice, the section. Okay, so what's the analogy? This is kind of like an inner product of a vector in a direction. The A's determine the tilt of my hyperplane. And, you know, if I had a centrally symmetric body like this, right, what would the central section be that determines the tilt of this area? So this is like a kind of fundamental theorem of calculus, right? This P power, when it's -1, it explodes, but I'm averaging over some small interval. You can prove this by various means, but essentially what you do when you're looking at this P power density, you can think about a kind of thin slab around this central slice. And what you get is a slice. So you can see polar bodies, which involve things like the soup, which are one-dimensional projections. You vary this P. You leave the convex world, P goes below 1, and at -1, you see sections. Okay, so here's a family of bodies that in a sense sees operations in Brunn-Minkowski theory, projections, convex bodies, duality, genuine polarity, duality, convex operations. And when P goes below -1, you start to see star-shaped things in general, things that are not convex, and at -1, you see slices. Okay, so they introduced this family and proved an isoperimetric theorem, again, that has some GLN invariance. Okay, I have the notion of duality here. I'm not allowed to shift, but I can take invertible linear transformations. This will be invariant. And it says if you want to maximize the volume of the dual LP centroid body, you cannot do any better than taking a ball of the same volume. Okay, so the equality case are origin symmetric ellipsoids. The P = 1 case has to do with centroid bodies. Centroid bodies are very related to the Busemann random simplex inequality for the same reason that determinants show up when I have random simplices, right? If I have a random simplex anchored at the origin and I have the triangle with 3 points, right, with x1 and x2, it's a multiple of the parallelepiped. Okay, but I can, instead of thinking about triangles, I think about parallelograms. I can also keep adding segments to this, and I get a class of bodies that's very related to centroid bodies. Okay, more on that in a little bit. But the P = 1 case is something connected to the objects at the beginning of the talk. The P = infinity case is a standard dual construction of your body, and there's also a famous extremal inequality known as the Blaschke inequality, which exactly says this. And the Lutwak-Zhang theorem, in a sense, puts all of this in one scale. Okay, so there's P = infinity. It's a known inequality. P = 1 here is very much related with the story about Busemann and Petty that I mentioned at the beginning. The Lutwak-Zhang theorem is really treating all of the P's in between 1 and infinity. Okay, and this is the Blaschke theorem. Okay, it's exactly just this statement at the endpoint. And it stops at 1. Okay, so this is a theorem which you can guess what it uses. The answer is always Steiner symmetrization. But the Steiner symmetrization here happens to depend on the parameter P, and it's important that these are convex bodies. Okay? I already explained how you can keep going to -1. Here you see the Busemann intersection inequality, right? About slices to a power n averaged on the circle. And then the question is, what happens in the middle range here? Okay, the -1 case is a known extremal inequality maximized on balls. For every value of p bigger than or equal to 1 is a known inequality extremized on balls. There's a gap in this interval. Okay, so that is the one I want to address. And the Lutwak-Zhang theorem is this one, right? I'll write it just for good measure. Polar maximized on K star. Okay, and I will address this one. And the objects that, I have sort of phrased all of these things as extremal inequalities about sections or projections. Behind the scenes are core notions in convexity called projection bodies, intersection bodies. The Busemann intersection inequality is something proved in the 50s, but actually it took some decades to understand the role of a body behind the scenes and its role in some of these volume comparison problems. This has to do with the class of intersection bodies introduced by Erwin Lutwak, developed and studied by Koldovsky and many others. So behind the scenes are bodies that actually satisfy extremal inequalities, and I have stated just the inequalities, but there has been a lot of research in connecting the bodies involved in this range between -1 and 1. Okay, so what has not been treated is the isoperimetric problem. Okay, so I mentioned some results here about volume comparison problems for this class of objects where I now have this parameter p. Many of these questions actually have sort of an older history in the sense that you can think about origin symmetric convex bodies as unit balls of Banach spaces, and there are old questions about isometric embeddings of LP spaces or isomorphic embeddings of LP spaces. And these questions have also been asked since the 20s, going back to Levy, Kinchin, Bachner, about embedding in LP spaces even when P is less than 1. Okay, so this is another thing that will make an appearance later in the talk, but along these lines, studied from a geometric perspective, Kalton and Koldovsky studied the class of bodies in between this range, and other geometric questions by Haberl and Ludwig were considered sort of dual operations to valuations in convexity, but now working with radial operations. Okay, so there's a bunch of work around the sets in this range, but the isoperimetric inequality is unsolved until, okay, some recent advances which I want to report on today. Okay, so I repeat, part 3 is complete. I set up a world of projections, world of sections, non-convex range in between. Maybe I should emphasize that the two inequalities that I started with, the Petty projection inequality is essentially here. Okay, there's an equivalent inequality that you can get one, you can get the other, and this is in a survey paper of Erwin Lutwak. The Petty projection here is really here. The Busemann random simplex inequality is around this p equal 1. The Busemann intersection inequality is here. So those are two inequalities that just have to do with convex bodies. They both have a common root, which is a probabilistic flavor. You prove something about random simplices, and you use that to prove these two endpoints. The Lutwak-Zhang theorem doesn't have a probabilistic connotation. It does not use the Busemann random simplex inequality. It's a direct analysis of these bodies themselves. Okay, so the end inequality is sort of, these two have a probabilistic flavor. The other ones are a direct analysis. Okay, and so the idea to go back to this range, in a sense, is to sort of revisit the probabilistic descriptions. Okay, so part 4 of my talk will be how to deal with this. And I will go back to a probabilistic model for thinking about how to generate these sets. Okay, so LP centroid bodies I introduced as something you attach to a convex body or a star-shaped set. These things have also been attached to probability densities. This is also a fruitful line of research. For example, Grigoris Paouris, who is a collaborator on several of these projects that are longer running with myself, he introduced the notion of LP centroid bodies that you attach to densities. For p bigger than 1, these are convex, so I can either write down their polars and write down the the dual norm of these or the bodies themselves. So you choose where you put the polar. Since I'm only dealing with polar objects in this talk, I put it here. Okay, so this is, you know, the reason to attach an LP centroid body to a density. You can think of, you know, if you have a measure on Rn, comes with a density F. What does the LP centroid body capture? It encodes some information about the linear functionals. So if you want to understand a measure on Rn, it's a fruitful idea to go through its linear functionals and its moments, right? So the LP centroid bodies have this parameter P. When P goes to infinity, the dual ones go to the dual body. If I put the polar on the other side of this identity, I would just get the body K back. Okay, so it's some family of bodies that interpolates between K and, you know, the centroid body. Okay, so once you have this probabilistic view, it's also very natural to attach a kind of empirical analog. Okay, so the body itself is defined using an LP norm. It's a true average. It's an LP integral with respect to this measure. You could also attach an empirical analog, which says take n random points according to your density. Maybe you have a convex body and you just, you know, sample n points. What would be the natural empirical definition of a centroid body? I'm not going to integrate. I'm just going to average these linear functionals at this point u. Okay, so I have n random vectors in a convex set. And instead of the true average, I work with the empirical average. So geometrically, what does this mean? I drew you a picture of the L1 centroid body. That's the ambient body is K. We saw the centroid body inside before. And now I claim you can generate the body, right? This curve inside empirically. How do you do it? Sample a point. It's a blue one. Take its negative. That's a segment. Sample a point. Take its negative. It's a segment. Keep doing this. Random segments and take their Minkowski sum and average by 1 over n. So what are you doing? I have the 3 blue points. Those are endpoints of segments. What's the center of mass of those 3? It's the red point. So it's like building up the centroids, but doing it empirically. Okay, so you trade working with the usual measure for this empirical measure. And if I do this with a dense set, of course, I'll get a good approximation by the law of large numbers. Okay, so the empirical centroid body, I trade the integral for an average. And what it corresponds to, if I want to generate the centroid body, I do it just empirically, right? Compute centroids, but using discrete point sets instead of the whole measure. Okay, so this is a project we started some time ago for dealing with LP centroid bodies. They're duals, the original ones, for p bigger than or equal to 1. It's a method that says if you have inequalities for centroid bodies like this, you can randomize them, attach some random process, and prove something for a random approximant of these bodies. Again, it uses, you can guess, Steiner symmetrization. Now I'm doing this with the class of functions, maybe symmetrization of functions. It also uses convexity, the fact that p is bigger than 1. Okay, but it turns out that this random description has some advantages in terms of analysis, that you can work with a random description to treat the p less than 1 case. Okay, so here's a theorem, also joined with Dario Cordero Arasken, Matthew Fredolisi. And what it is a kind of stochastic version of the Lutwak-Zhang theorem. Okay, so for this dual LP centroid body, you have this random approximation. And what it says is, you can approximate all these bodies randomly with the parameter n. Okay, and on average, you have an inequality that goes this way. Okay, and when n goes to infinity by a law of large numbers, I see the dual LP centroid bodies, I see the Lutwak-Zhang theorem. Okay, so it's an inequality that holds not only in the limit, but as you do this random approximation in a body and in a ball, these things both converge to two bodies, which are the original things in the Lutwak-Zhang theorem. Okay, so I stated this now not for sets, but for functions. So I can rearrange sets, right? K became K star. It was just a ball. I do that by iterated Steiner symmetrizations. You can also rearrange functions just by a standard definition of the symmetric decreasing rearrangement. Function which is radially symmetric, decreasing, and equimeasurable, right? I construct that just by rearranging the level sets of F. Okay, so for p bigger than 1, you have this empirical way of thinking about these objects. And now I'll move to the corresponding definitions when p goes below 1. Okay, questions? I didn't have a pause This is part 4, so I won't have another pause if I follow my system. So I'll pause now. Any questions? P goes below 1. What do I see? I start to see star-shaped things in general. So before I said these are dual to centroid bodies, I said a formula for the polars. I wrote a polar. I want to emphasize that when P goes below 1, it's not the dual of something. It's not a convex operation. So I changed the symbol. I traded the circle, which denoted polarity, and the bodies were genuinely convex and duals of something, for a diamond. And the diamond suit in LaTeX has this kind of LP wall where P is less than 1. Why not use that? So I define this object, which is a dual LP centroid body, but I mean dual in the broader sense of dual Brunn-Minkowski theory, not that it's a dual or a genuine convex polar. Okay, so this is the reason for the symbol change. Otherwise, the definition is the same. Deterministic body attached to a function. Empirical body attached to n vectors. Same averaging process. As long as these moments exist, the definitions make sense, and I still have a law of large numbers to get the empirical one converging to the deterministic one. So when P is 1, we know the P norm is convex. The dual centroid body is convex. The K here is a star, right? When P goes below 1, half, you start to see it's not convex, and it gets worse the smaller you take P. Okay, so now here's a family of objects, star-shaped objects that follow this family of bodies, but I'm starting to address this range. Okay, so it turns out you can actually deal with the random versions of these, and this is the main result. So it's a theorem with Adamczak, Grigoris Paouris, myself, and Paul Simanjuntak, who is a PhD student at the University of Missouri. He graduated, he's now a postdoc at Texas A&M. So I state first the random form. For these random objects, where I have now defined them analogously, but I have left the convex world, you still have an extremal inequality. It's still best, if you want to optimize this thing, to take the radially symmetric decreasing rearrangement of your function. In the class of star bodies, it's again just balls are the extremizers, or again, you have origin symmetric ellipsoids as a equality case, but I don't characterize the equality case, okay? Right now, just the inequality, but it's a sharp inequality. And when n goes to infinity, you get back a deterministic statement without any sort of random connotations. Just the random objects converge almost surely to deterministic objects, and these give back this inequality. Okay, so this is 2 years ago finished. I actually still don't know a direct way to deal with the non-random bodies. The proof that we use goes through the random ones. Okay, so I want to emphasize why you can treat a volumetric problem for the random one. What's the ingredient that makes the random version, you know, sort of susceptible to some similar line of reasoning as what happens when P is bigger than 1. Okay, so let me fill this in just so it's clear what's being proved. All of the 0, 1s are good. Some of the P's in -1, 0 are good. I don't know how to do them all because our proof uses some technical condition. And as long as n over P is an integer, we have an argument that works for those bodies. Seems like something purely technical, but okay, don't have it for all. Where did this project start? So the idea to, you know, like Sylvester's problem is something very old about random triangles, mean values. This is as old as geometric probability. Another place in which random constructions are used is in Banach space theory. Okay, so Gluskin in the 80s solved the long-standing problem about how far apart Banach spaces in n dimensions can be. So how do you measure how far apart they are? You use Banach-Mazur distance. What does this mean? Think of the unit balls in 2 n-dimensional norm spaces and try to sandwich one inside the other and reverse that and minimize the homothety ratio over all invertible linear transformations of these norms. Okay, you want to exactly measure, you know, the distance between the in radius of a ball and then sandwich it in between these two, minimize the homothety ratio, and then you're free to choose your position. Maybe you want to apply some invertible linear transformation to your square to really minimize this homothety ratio. That's the Banach-Mazur distance. So it's a long-standing problem how big this can be among n-dimensional spaces. So Gluskin had the idea to construct spaces randomly. How does he do this? He took a Gaussian matrix, just independent Gaussian vectors, and hit the L1 ball with it. What do you get if you just the L1 ball is the diamond, right? In L1. So hit this with the Gaussian matrix in a big space, in a high dimensional space. What do you get? Convex hull of a bunch of Gaussian vectors, something with spikes. It's still a convex set, but it turns out to be very hard to sandwich two independent copies of those, one inside the other. And a heuristic for why that should work, if you take a Gaussian matrix and you act from L2 to L2, you apply it to a Euclidean ball and then measure the diameter in a Euclidean sense. It's a well-controlled norm. Do the same thing when you go from L1 to L1. It grows up by a factor, by a factor. It's really a bigger norm. So his idea is put that randomness in the space. And this is how he constructed Banach spaces very far apart. Absolutely a method with far reach, okay? There's a survey paper by Minkiewicz and Tomczyk-Jagerman in the Handbook of the Geometry of Banach Spaces on the use of this method in finite dimensions and infinite dimensions as a source of counterexamples in Banach spaces. Nicole had a paper called Pathology is Everywhere. So once you start to see these exotic counterexamples, they work in many places, okay? So as Lena mentioned, my advisor fortunately passed away a couple of years ago. Very much motivated by how you think about objects in Banach space theory is how you generate these sets. You know, the isoperimetric problems I'm talking about are a totally different world than the Banach space problems, different functions, different invariants, but the perspective is what we really use to generate these sets and what started this project. Okay, so it's not methods, but the point of view, how to think about generating spaces using operators in norm spaces, acting on LP spaces, for example. Okay, so I'm good for time, right? So I will think about a matrix where I have column vectors sampled according to a density F. Take them in a convex body if you want. I'll fill them in as columns. And now I'll revisit the operations that I started with, things like random triangles or convex hulls, simplices. Those are linear images, right? Imagine I just applied a matrix to the standard face of a simplex. Well, when a matrix hits the ith column vector, I get the ith column of the ith basis vector, I get the ith column of the matrix. So I turn the convex hull of a face of a simplex, a standard one, to the convex hull of these points that are the columns of the matrix. What happens when a matrix acts on the cube? It's a set of linear combinations of the columns where the coefficients come from the cube. Minus 1, 1, that's a sum of linear combinations of segments. So I can start to reinterpret the operations you saw involving convex hulls, Minkowski sums of segments as linear images. You lift, hit this body with a random matrix, right? And that generates your random set. These things can act on LP spaces, right? And I can take their polars. Okay, so empirical dual empirical LP centroid body I get by taking this matrix, hitting the LQ ball where P and Q are conjugate and taking their polar. Okay, this is all of the objects I said. Essentially, you can encode as linear operations, either as a image or pre-image under a random matrix. Okay, so I'm going to use the same idea, but I'm going to start to adapt this to the non-convex world. Okay, so same matrix. And, you know, I started this motivation by saying this is something about duality, but duality outside the class of convex sets, right? We know the polar of a projection is a section of the polar. That was for orthogonal projections, but I could just as well work with a linear map, a long matrix that's like a projection. The polar of an image, it's going to be a pre-image of the polar. Okay, that's exactly the same statement that I said before to a scaling factor associated with X by polar decomposition. So duality again motivates such an identity, but I could just as well think about sections of star-shaped sets. So duality may have got me here, but then I'll just forget that duality got me to these relations. Why don't I just think of taking this matrix, not projecting on some space, but taking the transpose and thinking about it as an embedding. Then the transpose comes with some lower dimensional subspace, and I'll just slice an LP ball. And formally, you look at what happens for this empirical LP centroid body. It's an LP norm, and I want a vector of inner products of my columns. I traded my X for the transpose to be in an LP space. It's a slice of LP where P is now less than 1. Okay, so I was working on this project in Calgary in the summer, and I saw this beer by the establishment brewing company called Jamrock with the LP ball, and I was really working on this. So this is the official beer of this project. I recommend it. That's the description of the set. How does this help you? Now it's just a description. I still don't have methods that deal with the non-convex world. So that's the last step. Okay, so I use a volume representation. Okay, so anyone familiar with Gaussian integrals knows and dimensions, it comes with a covariance matrix, that's some ellipsoid. The determinant, right, comes out of that computation, but a volume of some ellipsoid is really this exponential integral. You can play the same game, not just with ellipsoids, but with other sets, just sort of polar coordinates with respect to a body. So I can write the volume of a section of LP with this basic formula, just integration on level sets. It's the gauge or the norm function I had defining these LP centroid bodies. And they come with a power P, which is less than 1. Now, there is a nice family of random variables that lets me trade powers P less than 1 for other powers in the convex range. And this has to do with stable random variables. So we'll call a random variable stable if whenever I take a linear combination, phi d copies of that, I have the same distribution up to scaling and shifting. And these things come with the parameter alpha. And what you can characterize this family of random variables through their Laplace transform. And if I have the Laplace transform in this probabilistic language, what I get is a functional like this, e to the minus t to the alpha. So very much related to Bernstein type theorems and completely monotone functions, very similar representations. But the nice thing about such a formula with this range of alpha is that I have traded a power t for a power 1, right? The alpha here is less than 1. And I'm going to trade it through this representation for powers less than 1. So what happens in the volume formula if I see a p less than 1? I'm going to just tensorize, write this product separately, and do such a transformation on each p. So this is an idea proved in a recent formula for volume of sections of LP in the non-convex range by Nair and Koch, who used this change of density argument. I explained this to a harmonic analyst in Missouri, and he says, oh, yes, this is superposition of Gaussians. Use this in singular integrals. You name your language. P-stable, change of density, Bernstein theorem, however you want to call it. It is a method to trade powers in a non-convex range for convex ones at a cost. And the cost is this extra averaging. What's the effect of averaging? Okay, so there's a complicated formula here, but the spirit of this is if I see a function like this with the t to the p, I can trade it for power 2, the small variable change, at the cost of averaging. Okay, this extra integral in this Xi random variable. So if the p was at 2 in this formula, it would be an ellipsoid, which comes with a determinant, which is not so different than the quantities we started the talk with. Assuming I can do this for every fixed choice of these random variables, but this is a Fubini. I have an expectation for the volume, and I'm allowed to do this sort of pointwise. Okay, so you can turn this nice formula that they proved about sections. They proved it originally for sections of L1 and explained that you can do this for the non-convex range. And this turns out to be what the crucial thing is in this ingredient. And the empirical form, right, lets you tensorize. And then I'm dealing with just real values, right? I'm not dealing with this sort of integral, right? So I do this in the empirical form. I trade the non-convex problem for a convex one, and then I can use the convex methods, okay? This symmetrization machinery we develop for images, pre-images of sets. So, okay, that's, I think, a good place to end.
Yes, go back to the definition of stable, please.
So Gaussians have this property, right? But if you start to relax the integrability conditions of your random variables, that they don't have a finite variance, then there are other limiting laws, and these are the distributions that come up. And there's different ways to introduce them also for complex numbers, but okay, these are the exact ones that I need for this.
I'm curious about the probabilistic techniques part. So I guess it's not necessary to consider possibly sample data that are not independent. But do you think if I sample this x1 to xn, not IID, but maybe with some kind of repulsion, that will still maintain the limit to the empirical distribution? Do you think that would still?
So I think, like, there's two questions here. One is like, what's the limiting object and what are the conditions that you still get the right limiting object? And it's possible that there the independence may not be like necessary, right? You can think of laws of large numbers where you relax both the independence and the identically distributed part, right? The real question is like, what can you do in the symmetrization step if you relax independence? So, you know, I mentioned like all these problems are sort of iterated integrals. They're naturally on a product space, which comes with some independence. And in actuality, what you use are kind of rearrangement inequalities for products of functions. So what these have built into them is a product structure. So the symmetrization step kind of demands a product structure which says independence. It's possible that there are modifications of these rearrangement inequalities, but then that's a separate question and actually I think quite interesting, like from a geometric perspective, right? Like the describing the object is one question, and then proving something for the one where you have relaxed this independence, that's another question. And interesting, but I don't have an immediate, you know, way to deal with that.
So you're still working on the negative case with other methods, or you're still
yeah, they're
thinking it's going to be one theory between -1 through this?
I think it's a purely technical thing. Right now, it's like a tensorization trick. When n over p is an integer, you have this many integrals, you can collapse them in one. And, you know, we tried several things to try to kill this condition, but I think it's just a technical thing that we haven't, you know, reduced it to this case or found the right trick or representation. I mean, it's the kind of thing that if someone comes with a representation, it might make it easy. But if you don't know the representation, what's the way to attack it, right?
If not, let's have the speaker again, and then
Oh, there's a chat.
was it the chat?
Oh, awesome talk. Okay, cool. Thank you.